Hello, future engineers, subscribers, viewers, and students. There is another video in plane and solid analytic geometry, particularly on the topics on ellipses, hyperbolas, equation of the diameter of conics, and tangents and subnormals. So, the topics to be considered in this video are the following: ellipse, hyperbola, equation of the diameter of conics, and subtangents and normals. So first, let's consider an ellipse with an eccentricity that is less than 1. So we define an ellipse as the path generated by a moving point so that the sum of its distances from the foci is always equal to the length of the major axis, which is 2a. So to derive the equation of the ellipse, so let's have the elements of the ellipse. First, let's consider the center of the ellipse at the origin, as shown in this figure here. So we have here the foci at negative c comma 0, f1 and f2, c comma positive 0. The vertices v1 at negative a comma 0, that's the moving point on the path or on the curve on the ellipse x comma y, and the distance of that point from f1 is denoted by df1. Its distance from f2 is denoted by df2, and by the definition, df1 plus df2 equals 2a. So these are the directrices. The distance of the left directrix from the y-axis is d. So the equation is x equals negative d. For the right directrix, the equation is x equals d. So distance from the center is d, as shown. Then we have the vertices d1 at negative a comma 0. So its distance from the origin is a, that vertex 1. d sub 2 is at a comma 0. d sub 3 at 0 comma b. d sub 4 at 0 comma negative b. So the starting equation df1 plus df2 equals 2a. By distance formula, df1 is square root of quantity x minus negative a, so x plus a square plus y minus 0 square. And when the moving point is at d3, because the sum of the distances is 2a, and by symmetry, the distance of d3 from f1 would be a, d3 from f2 would also be a, as shown the figure. And since this is b, then relationship between or among a, b, and c would be a squared, the longest, is equal to b squared minor semi-minor axis squared plus c squared. So again, square root of x minus negative c, so x plus c squared plus y minus 0, y minus 0 squared, plus df2 square root of x minus c quantity squared plus y minus 0 quantity squared, which is just y squared, equals 2a. So we are going to transpose this to the right and at the same time expanding. So this left here radical is square root of x squared plus 2cx plus c squared plus y squared equals 2a minus square root of x squared minus 2cx plus c squared plus y squared. Then we square both sides. So we have to remove the radical sign in the left side. In the right side, square of the first and twice the product, so negative 4a square root of, we just copy this, then square of the second, so we just remove the radical and copy the terms inside the radical. So we have x squared plus 2cx plus c squared plus y squared equals 4a squared minus 4a square root of x squared minus 2cx plus c squared plus y squared. Then the square of the second, we just remove the radical and remove the sign. So we just copy all these terms here. X squared minus 2cx plus c squared plus y squared. So we can cancel x squared, c squared, y squared. So we have here in the left side, we transpose this to the left. So this becomes 4a square root of x squared minus 2cx plus c squared plus y squared equals 4a squared minus 4cx, because we canceled x squared, c squared, and y squared. So 4a square root of x squared minus 2cx plus c squared plus y squared equals 4a squared minus 4cx. Cancel out 4 also. This is common to all terms. So the expression reduces to this. So the equation reduces to this. Next, we square both sides. And this becomes a squared quantity x squared minus 2cx plus c squared plus y squared equals a to the fourth minus 2a squared cx plus c squared x squared. Expand. So a squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared equals a to the fourth minus 2a squared cx plus c squared x squared. So we can cancel negative 2a squared cx. Then we have here a squared x squared, in the right side c squared x squared. We factor out x squared. So we have x squared quantity a squared minus c squared. Then we just retain a squared y squared. And for these two terms, the left side a squared c squared, in the right side a to the fourth common a squared. So we have in the right side a squared quantity a squared minus c squared. So again, x squared times quantity a squared minus c squared plus a squared y squared equals a squared quantity a squared minus c squared. And since at V3, we have these relations that a squared equals d squared plus c squared. So therefore, a squared minus c squared, a squared minus c squared is d squared. We replace this by b squared. So x squared b squared equals a squared y squared plus a squared b squared. Dividing everything by a squared b squared. So we have x squared over a squared plus y squared over b squared equals 1. So this is the standard equation of an ellipse with center at the origin and major axis coincident with the x-axis. So that's it for that standard equation of ellipse. And we use this to pattern or to write the equations of ellipse with center at the origin and major axis on the y-axis, and for the cases where ellipses have their centers at h, k. So the major axis is v1, v2, and it is equal to 2a for the ellipse. So let's have this ellipse with center at the origin, major axis on the x-axis, call that ellipse number 1. Then ellipse number 2, center at the origin, major axis on the y-axis, call that ellipse number 2. Ellipse number 3, with center at h, k, and major axis parallel to the x-axis as shown. So, ellipse number 3. And ellipse number 4, center at h, k, major axis parallel to the y-axis as shown. So again, we note that V1, V2 is the major axis and it is equal to 2A. V3, V4 is the minor axis which is equal to 2B. And F1, F2 is the distance between foci and it is of length 2C. And distance between the rectrices is equal to 2D. So for this ellipse here, equation 1, its equation is, because major axis on the x-axis, center at the origin, its equation is the derived equation just recently, x squared over a squared plus y squared over b squared equals 1. For ellipse number 2, a squared should be under y squared because the major axis is on the y-axis, center at the origin. So for ellipse number 2, the equation is x squared over b squared plus y squared over a squared equals 1. So in other words, a squared is under the axis that is squared where the major axis is parallel to that axis. So ellipse number 3, because the center is now at h comma k, major axis is on parallel to the x-axis. So it is x minus, we just replace x squared here by x minus h in general, then y by y minus k. And since the major axis is parallel to the x-axis, so we just follow this equation. So x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. That's for ellipse number 3. And for ellipse number 4, we just follow this and replace x by x minus h, y by y minus k. So under x minus h quantity squared is b squared. So that's it for this part of the video. So from the general equation of a conic, if you can recall, it was ax squared plus cy squared plus dx plus ey plus f equals 0. We detect or recognize that this conic is an ellipse. Take note that both x squared and y squared are present and have same positive signs. So when the signs are positive, remember that for a circle, they are equal. The signs are also the same. So therefore, this represents an ellipse if the product A and C, AC is positive or greater than 0. So that represents an ellipse if AC is greater than 0. And the semi-major axis, A, is greater than both semi-minor axis B and half of the distance between foci. So A is greater than B, comma C. When P is at D3, so let's draw the ellipse first. So these are the vertices. And when the moving point is at V3, the distance of this moving point from the focus, one of the foci, is A, and its distance from the fixed line is D. So therefore, eccentricity is A over D. We define it as A over D also. That's it. So eccentricity is A over D. When the moving point P is at V2, so when it is here, the distance of this moving point from the focus is A, because this is A, minus C. So this is A minus C, while the distance of this point from the directrix is D minus A. So eccentricity is also defined as A minus C over D minus A. Cross multiply, DE minus AE equals A minus C. And we take note that D times E is A from this relationship. So A minus AE equals A minus C. We cancel out A. So we have negative AE equals negative C. We cancel negative 1. So that means eccentricity is also C over A. Another definition of eccentricity, C over A. But because D is A over E from this equation, and we replace E by C over A, so D is equal to A over C over A. Therefore, D is also the distance from center to the directrix is A squared over C. Or because I live in Davao, DC means Davao City, A squared means Ato, A2, Ato. So just to have mnemonic aid to memorize the relationship. You can easily memorize this relationship if you derive all these elements by your own also. Then, important relationship, A squared equals B squared plus C squared. By the way, the eccentricity E prime is called second eccentricity if A here is replaced by B. So E prime second eccentricity is C over B. It's not written here, but you might encounter that in the future as a problem. Then second eccentricity, remember, is C over B. So another relationship among A, B, and C is that A squared equals B squared plus C squared. From this right triangle, A is the longest, so A squared equals B squared plus C squared by Pythagoras theorem. Then let's have the length of latus rectum. We define latus rectum as a line segment perpendicular to the axis, in this case major axis, through the focus. So this is the latus rectum. And because the ellipse is symmetric with respect to the major axis, the coordinates of this point would be, call this L, C comma half of the length of latus rectum, LR, and for the lower point R, C comma negative LR over 2. Since these points lie on this ellipse, and this ellipse is has the equation x squared over a squared plus y squared over b squared equals 1, and we can derive the length of the latus rectum. So at L, which is at C comma LR over 2, substitute into the equation of this ellipse with center at the origin. X squared over a squared plus y squared over b squared equals 1. We replace C by x by C and y by LR over 2. So we have quantity LR, C squared over a squared plus LR over 2 quantity squared over b squared equals 1, which is LR squared over 4b squared equals 1 minus C squared over a squared. The right side is a squared minus c squared over a squared, cross multiply. So LR squared equals 4b squared times quantity a squared minus c squared over a squared. And since a squared minus c squared from this relationship is b squared, so we replace this by b squared. So LR squared equals 4b squared b squared over a squared. LR squared therefore is 4b to the fourth over a squared. Extracting the roots, so we have LR equals 2b squared over a. So the length of the latus rectum of an ellipse is 2b squared over a. So I hope you can remember that, derive it by your own so that you can easily memorize the length of the latus rectum. So let's have the physical properties of ellipse. One is the area of ellipse is pi AB, just like area of circle, pi r pi r squared. So for the ellipse, the area is pi AB. The perimeter, these are approximate formulas. So one is perimeter of ellipse is 2 pi square root of quantity a square plus b square over 2. So just like for the circumference of a circle, 2 pi square root of r square plus r square over 2. So it is equal to square root of r square, which is r. So 2 pi r. Then another formula, this is approximate, but I think this is more accurate because it involves 3 terms. So it is 2 pi square root of a square plus ab plus b square all over 3 because there are 3 terms in the numerator. But you just familiar or memorize this formula, approximate formula for the perimeter or circumference of an ellipse, 2 pi square root of a square plus b square over 2. You can easily memorize this another formula. They are not equal, but this is more accurate supposedly. 2 pi square root of quantity a square plus ab plus b square all over 3. So 3 terms in the numerator, so this should also be divided by 3. Then for the third physical property, the angle of incidence is equal to angle of reflection. That is, this may be a gallery for debates. If one debater is at focus 1, then we have sound wave which travels and hits the inner surface of this elliptical surface. It will bounce, that sound wave will bounce towards the other focus and vice versa. So this may be the sound wave, then it will reflect to the other focus. Another case will reflect to the other focus. In the same manner, if the person is positioning at f2 and he speaks, then the sound wave would reflect towards the other focus. So that's the third property, angle of incidence equals angle of reflection. So that's the angle of incidence, that's the angle of reflection, same, equal. We then proceed to the next conic, which is a hyperbola, and a hyperbola has an eccentricity greater than 1. We define a hyperbola as the path generated by a point moving so that the difference of its focal distances is constant and is equal to the length of the transverse axis 2a. So let's consider first a hyperbola with center at the origin and define all its elements, such as the vertices, foci, then the asymptotes. So this is the rectangle where the asymptotes are the diagonals of this rectangle. The center intersection of the asymptotes is the center, and in this case it's the origin first. So that's semi-transverse axis A. So the branches of the hyperbola would be open to the left and to the right for this case. And we'll just pattern the other standard equations of hyperbolas. So that's the vertex at negative a comma 0. The other vertex is at positive a comma 0. Then we have vertex 3 at 0 comma b. The distance of the line segment V3B for V sub 4 is the conjugate axis, and that is equal to 2b. Now these are the asymptotes, and the length of the semi-conjugate axis is b. The total length is 2b. And the diagonals, half of the diagonal of this rectangle is c. This is also c. So that's also the radius of the imaginary circle circumscribing the rectangle, so that the foci will lie on the circle and on the x-axis, as shown in the figure. So that's the left focus at negative c comma 0, and the right focus at positive c comma 0. And the point, we draw the hyperbola first, but before that, let's have the length of the latus rectum, left and right. So these are the red curves, are branches of the hyperbola. And we select a point on the hyperbola. We denote that by x comma y. Then its distance from the left focus is d sub f1, and its distance from the right focus is d sub f2. And by the definition, df1 minus df2 equals 2a. So that's the asymptote 1, asymptote 2. Directrices would be closer from the center, and the distance is the same, vd. So this is the starting equation, df1 equals df2. So df1 equals 2a plus df2. And df1 is square root of x plus c quantity square plus y minus 0 quantity square equals 2a plus square root of quantity x minus c quantity square plus y minus 0 quantity square. So square both sides, then we simplify the resulting expressions in the same manner as in the derivation of an ellipse, as we simplify after we square both sides, equation on an ellipse. Then we will arrive at this equation here, x squared over a squared minus y squared over b squared equals 1. So which is the standard equation of an ellipse with center at the origin, transverse axis on the x-axis. So remember, for the ellipse, it was x squared over a squared plus y squared over b squared equals 1. So I don't need to derive this equation in the same manner as we derive the standard equation of an ellipse with center at the origin and major axis on the x-axis. It's the same. You just derive this by your own, so that you will know how to derive the standard equation of hyperbola. So this is the resulting equation. And this time, if you look at the figure, C is longer than A and B. So that's why the relationship is now C squared equals A squared plus B squared. Remember that in ellipse, it was A squared equals B squared plus C squared. But for hyperbola, C is the longest, so C squared equals A squared plus B squared. So C is greater than A and B. A can be greater than B, it can be less than B, and it can also be equal to B. So again, A could be greater than, less than, or equal to B. When the situation is A is equal to B, the hyperbola is called equilateral hyperbola. So take note, when A is equal to B, the hyperbola is called equilateral hyperbola, and the eccentricity for that hyperbola is square root of 2. So it is still, eccentricity is c over a. You just replace b here by a, so c squared equals a squared plus a squared. So c squared equals 2a squared. So that's why c over a is square root of 2, which is the eccentricity. And it is greater than 1, of course. So that's it. Reminder that for hyperbola, a can be equal to b. It can be less than, it can be greater than b. So all formulas for the elements of an ellipse are the same for hyperbolas. So that is, eccentricity is still c over a, or a over d, D is still a square over c, and the length of the latus rectum is the same. So eccentricity c over a, d is a square over c, and length of latus rectum 2b square over a. So take note that these formulas are also the same for ellipses. The only difference is eccentricity for an ellipse is less than 1, while for the hyperbola greater than 1. Then from the general equation of a conic, we should be able to detect or to identify that the given general equation represents a hyperbola. So we notice that the coefficients of the second degree terms are opposite in signs. So ax squared plus cy squared plus dx plus cy plus f equals 0. This time the coefficients of x squared and y squared are opposite in sign, so therefore the product is negative. So this equation represents a hyperbola if the product a and c is less than 0 or ac is negative. So just like for ellipses, the name is now different. D1 distance D1 D2, the line segment V1 D2 is 2a, and it's called transverse axis. D3 V4 is equal to 2b, and it's called conjugate axis. 2d distance between directrices, and 2c distance between foci. So let's write in general the standard forms of equations of hyperbolas. So when the hyperbola has its center at the origin and transverse axis on the y-axis as shown in the figure, then the equation of the hyperbola is y squared over a squared minus x squared over b squared equals 1. So it is automatic that the positive term in this standard equation has its denominator a squared, regardless of a squared is greater than, less than, or equal to b squared. Remember that for hyperbolas, a can be equal to b, less than b, or greater than b. So automatic, because the transverse axis is on the y-axis, then the squared term would be y squared, and the denominator is automatic a squared. When the center is at hk and transverse axis parallel to the y-axis, and if it is here, the center is at the origin and transverse axis on the x-axis, so it is x squared over a squared minus y squared over b squared equals 1. So for when the center is at h comma k, then it is x minus h quantity squared over a squared. This is always a squared, the positive term, minus y minus k quantity squared over b squared equals 1. And for this hyperbola here with center at h comma k and transverse axis parallel to the y-axis, so it is, we replace y by y minus k, x by x minus h. So y minus k quantity squared over a squared minus x minus h quantity squared over b squared equals 1. So that would be the equation. Then the trick in finding the equations of asymptotes. So remember that hyperbolas have asymptotes. So the trick is we simply replace from the standard equations. For instance, for this equation here, we simply replace 1 by 0. If this is the equation for this hyperbola, replace 1 by 0, then simplify the equation. Extract the square roots. Same is true with this. So replace 1 by 0 from the standard forms of equation of hyperbolas. Then simplify. And there should be two equations. One with positive slope, the other with negative slope. Then we proceed to the equation of the diameter of a conic. So we define how we have to do this procedure, although some of the procedures here would be involving differentiation from calculus. So how to determine the equation of the diameter of a conic? So these are the steps. First, we have to differentiate the equation of the conic with respect to x. So find dy dx, in other words. Then we replace dy dx slope or y prime by the slope of the parallel chords. So I'll define parallel chords in the figure here. Then the simplified form of the resulting equations is the desired equation of the diameter. So let's define, so for instance, we have a conic here, and coordinate axis x and y. Then we have parallel chords. These are the parallel chords. And then we join midpoints of the parallel chords. These are parallel chords. These are the midpoints of parallel chords. Then the line joining the midpoints of the parallel chords is the diameter of the conic. And this diameter of the conic is determined by following this procedure here. So differentiate the function with respect to differentiate the equation of the curve or conic with respect to x. Replace dy dx by the slope of these parallel chords, then simplify the resulting equation. So the last part would be about subtangents and subnormals. So let's have the conic first. So let us say that's the conic, and we have a point of tangency, which is at x sub t comma y sub t. Then the tangent line is drawn intersecting the x-axis. The horizontal projection of that tangent line is called the subtangent. So that's the tangent line, and the horizontal projection is what we call subtangent, as shown in the figure. Let's denote it by capital T sub S. While the normal, which is the line perpendicular to the tangent line through the point of tangency, and also will intersect the x-axis, that's the normal. And the point of intersection that the normal line intersects with the x-axis is denoted by a sub n, and of course y is 0. The horizontal projection of this normal line is the subnormal, denoted by capital sub n sub s. So we have similar triangles here. This angle of inclination theta is also this angle here. And take note the relationship of the slopes between the tangent and the normal. The slope of the normal is the negative reciprocal of the slope of the tangent, and vice versa. The slope of the tangent is the negative reciprocal of the slope of the normal line. So this is the subnormal, denoted by capital N sub S. So since tangent of theta is m, slope of the tangent, and from the figure it is equal to yt, because this is y sub t, over t sub s. And it is also equal to n sub s, by the way this is n sub s, over y sub t. So again, tangent theta is m, slope of the tangent line, equals yt over t sub s. It is also n sub s over yt. So The length of the subtangent therefore is, because it is always positive, it represents length, so it is equal to absolute value of yt over m, or it is also right x minus left x, so absolute value of x sub t minus a sub t, or absolute value of x sub t minus a sub t, because it is vice versa, a sub t minus x sub t absolute value. So t sub s has two formulas. Absolute value of yt over m, it is also equal to absolute value of xt minus a sub t. So you just look at the figure here. You don't need to memorize, actually. You just set up tangent theta opposite yt over t sub s, and from there you can define t sub s. It is also equal to the, because it is horizontal projection, so it is right x sub t minus a sub t. To make it always positive, so put absolute value back. As long as you write it right x minus left x, this is always positive. Likewise, n sub s is product, absolute value of the product of slope and y sub t. It is also equal to a sub n minus x sub t, absolute value. So it is absolute value of n times y sub t. It is also equal to a sub n minus absolute value of a sub n minus x sub t. Now, the technique in finding the equation of the tangent to the conic from analytic geometry's point of view, so it's very different from calculus. So if you are reviewing for your licensure exams, you may apply differentiation and replace dy dx as slope of the tangent to the curve. That is from calculus point of view. But for analytic geometry's point of view, we have to remember these suggestions, that we have to replace x squared by x times x sub t and y squared by y sub t. So remember xt yt would be the point coordinates of the point of tangency to the conic. Then if it is x, replace x by 1/2 of quantity x plus xt and y by 1/2 of quantity y plus y sub t. So that's the condition. So because we still have space here, let's solve one problem as an application of this video on this problem is about finding the equation of the ellipse. So general form, let's transform it to general form. Although if you express it in standard form, you can easily identify that it is an ellipse. Find the equation of the ellipse with foci at 4, -2, 10, -2, and a vertex at 12, -2. So let's plot all those points so that we can analyze about the expected equation of the ellipse. So the ellipse should have its major, because F1 and F2 lie on a horizontal line, so the transverse axis is parallel to the x-axis. So the ellipse would be as shown, and the expected equation of this ellipse is x minus h quantity square over a square plus y minus k quantity square over b square equals 1. So that's the anticipated equation of the ellipse, where the center is the center of the line segment joining F1 and F2, midpoint, and the midpoint formula is simply average of the coordinates. So 1/2, center is at 1/2 comma 4 plus 10 and comma 1/2 -2 minus 2, so that's -2 also. So 1/2 of 4 plus 10 is 7, center is 1 half of 4 plus 10, comma 1 half of negative 2 plus negative 2. So the center is at 7, comma negative 2. And the expected equation, before that, A is distance between the vertex and the center. So just the x difference, 12 minus 7 is 5. A is 12 minus 7, so 5. While C is 10 minus 7, so 3, or it is 7 minus 4, so it is 3, C. And because A square equals B square plus C square, 5 square equals B square plus 3 square, so B square is 4 square, or 16. Then the expected standard equation of this ellipse is x minus h quantity square over a square plus quantity y minus k square over b square equals 1. So substituting values of these elements, so we have quantity x minus 7 square over 5 square plus y minus negative 2 quantity square over 4 square equals 1. So we multiply everything by the LCD, which is 5 square times 4 square, 25 times 16, 400. So this is 16 times quantity x minus 7 square. So we expand directly. 16 times x square minus 14x plus 49 plus 25 times quantity y square plus 4y plus 4 equals 400. Distribute 16x square minus 224x plus 784 plus 25y square plus 100y plus 100 equals 400. Then simplifying, writing in the general form, equation of the ellipse is 16x squared plus 25y squared minus 224x plus 100y 784 plus 184 minus 400, so 484 equals 0. So the equation of the ellipse is 16x squared plus 25y squared minus 224x plus 100y plus 484 equals 0. So that's it for this video.